Greetings. We are continuing with our lectures on our discussions on heat pumps and refrigerators. And today I want to look at more real refrigeration cycles. So what we consider real or practical refrigeration cycles. So if we remind ourselves what we did in the last discussion, what we had in the last discussion, we remember that the temperature entropy profile diagram for the reverse Carnot cycle we had was temperature entropy, state point 1, 2, 3, 4, the anti-clockwise direction. So the area enclosed gives us indication of the work, and we captured this and said that step 1 to 2 represented isentropic compression. This was isentropic compression. This one here was an isentropic expansion. And this particular one was isothermal compression. And this one was isothermal expansion. And we had captured it in a much better sense when we said that when you move from low temperature, low pressure to high temperature, high pressure state isentropic compression, when you go from state point 2 to 3, we have release of heat through this condenser. We had a condenser there. And the state 3 to 4, we had isentropic expansion. And of course, we had evaporation from state point 4 to 1. And we had captured that and indicated that state point 1, we have compression. Then we had the condenser. State point 3. Then we had the expansion. Then of course, we had what you call Q41 for from state point 4 to 1. This one we had Q to 3. There we had, of course, W arc here is 1 to 2 is negative. This one, W3 to 4 is positive. Is positive. And here we have the whole storage, whole space. Whole storage. And so we had that type of a system for the reverse Carnot cycle. Here we have the condenser. Here we have the evaporator. And of course, temperature. And we had seen that in this particular case, the coefficient of performance, we've seen that the coefficient of performance, the heat pump, the mass coefficient, performance, the refrigerator, plus 1. And remember, we had also said that the coefficient of performance, heat pump was Q23 over W, and coefficient of performance, refrigerator was minus Q41 over W. Remember, it's negative work, so we had the negative sign that we get a positive value. Now, in reality, normally we remove the expansion machine and replace it with a throttle valve. In practical cases, we remove the expansion machine and replace it with a throttle valve. And so what does that mean? That now means that other than the isentropic process, now we are dealing with the case of an isenthalpic process. So let us just capture the new TS, the TS profile. In this particular case now, will be given by this shape. You have state point 1, state point 2, 3. Now we have state point 4. 3 to 4. Notice that we have replaced the expansion machine with a throttle valve. So let us capture that pictorially in a much more clear way, much more clearer graphical expression. So we are saying you have a state point 1, point 2, we have a condenser, once again is in Q 2, 3, because we have state point 1, and so we have here our throttle valve as the throttle valve. Anytime you see the word throttle, when you talk of throttling processes, those are isenthalpic processes where there's no change in enthalpy. In fact, one of the very famous experiments involving this throttling is the Joule-Thomson experiment, which we discussed in our earlier lectures. And so we have the throttle valve, and of course, we have our cold space evaporator in the cold space. You have the throttling valve. Now, we have replaced the expansion machine with a throttling valve. So now we are dealing, the step 3 to 4 is not isentropic, but is isenthalpic. Step from state point 3 to 4 is isenthalpic. That is, the enthalpy is constant. And we are seeing the new change. Now, what does that mean? Now we have removed the expansion machine. So it means that that work which is done on expansion is now not there. The work which is there is purely the compression work. Therefore, work is now purely compression work. Because you have removed the expansion machine there. And number 2, remember that when you have the throttle valve, what happens is that there's a decrease in pressure. And of course, when there's a decrease in pressure, there's an increase in velocity of the flow. The throttle valve results in decrease in pressure. But we have increased fluid flow. And so definitely what happens is that the Q41 now will be affected. The Q41 will be affected. Therefore, Q41 will be affected. And if it's affected, definitely therefore, the coefficient of performance, which was minus Q41 over W, is affected equally. It's affected equally. So it's no longer the same. And what's the reason? Now that the amount of heat extracted per unit mass is reduced. It's definitely reduced. That's basically what we are saying there. And so the kind of fluids which are normally used in this particular real refrigeration cycles, the fluids are normally ammonia, there's ammonia, methyl chloride, sulfur dioxide, and we can use Freon 12, Freon 2, we can use Freon. Now, these are the common ones which are used. Carbon dioxide has been used, but carbon dioxide, this question mark, has been used extensively, but there are pitfalls in terms of carbon dioxide in that it has very high vapor pressure and has low critical temperature. Remember, critical temperature is the point where you cannot separate between liquid and vapor. So if you look at the pressure temperature profile for the carbon dioxide, then you'll understand better. That's the carbon dioxide pressure temperature profile for carbon dioxide. That's the phase diagram for it. Then you'll see why that is so. That, of course, remember in our discussions, so that's the triple point. So you can just go through some of those early lectures on phase equilibrium, look at the phase diagram for carbon dioxide, and you'll see that it has very high vapor pressure and very low critical temperature. Critical temperature, T critical there. Or that T critical temperature. So in a nutshell, in real refrigeration cycles, the practical refrigeration cycles, we have replaced the expansion machine with a throttle valve. The throttle valve decreases the pressure, and then of course this increase in flow, and with this increase in flow, then we have less extraction of heat from that particular fluid, and of course that will affect the coefficient of performance in terms of the refrigeration cycle, which you have already seen in our earlier discussions. And the fluids which are normally used, like I said, is ammonia, we use methyl chloride, we use sulfur dioxide, we use freon, we use carbon dioxide is used, but that's very high vapor pressure, low critical temperature, and that means very expensive piping. So this means that you have to use very expensive piping. So you have to use expensive piping in the case of that. So we'll stop at that particular point and we'll pick up next time.